Hi everyone. Today we are going to start talking about how stars form. So in order to do that, we will learn about what is called the interstellar medium, how this relates to star formation. We'll talk about scattering, being able to explain how light scatters and why. And we'll look at different types of nebulae, so emission, reflection, and dark nebulae. So to start thinking about star formation, we have to start with what is called the interstellar medium, or ISM. So most of space, when we look up, it looks empty. So we see stars, but in between the stars, there is nothing. It's dark black. When in reality, there is actually quite a bit in between the stars, and that is what we call interstellar medium. So there is this ISM in between all of the stars all over the universe, but it is not visible at the visual wavelengths. So we can't see it at all. So that's why space looks mostly empty. This ISM is actually only observable at other wavelengths. So in the visual, we can't see it at all. So here is a picture of the sky with the asterism of Orion outlined. This would be what it would look like in the visual. If we were to look at this same area of the sky in the far infrared wavelength, we would see quite a bit of this ISM. So this interstellar medium that exists in between all over all of the stars in the sky. And we actually cannot see it with visual wavelengths. So interstellar medium, it's actually where stars are born. So in order to start talking about stars, star formation, star lifetime, we have to start with what is the interstellar medium. So it is the clouds. Where we have the most dense clouds of this ISM material is where stars are born. So it is outside of our solar system. So you'll see here's our sun. Here is our planets. And where we have the interstellar medium, and specifically the most dense areas of the ISM, is far outside of our solar system itself. So if we can't see this ISM, how do we measure it? So ISM, the interstellar medium, is essentially a cloud of particles in space. But we can't see it. How do we even know that it's there? How do we know that this exists? How on earth do we measure it if we can't see it? Well, what we can do is measure it indirectly. So we can actually measure how other things change due to the other things that we can see, how they change due to the presence of ISM. So we can measure the effect of light from stars as it passes through ISM, for example. So stars will appear fainter or completely blocked if there's a cloud of gas and dust, being the ISM, in between us, the observer, and that star. So for example, here we have visual wavelength observations, and we see that there is this blob of darkness. And what that is that's actually interstellar medium right there. We're seeing a cloud of this interstellar medium blocking the light of the stars that are behind it. So we call this interstellar extinction, where we see the ISM by actually observing the darkness that it's causing. We're only observing that it's blocking something else. We can't actually see the ISM itself. So here are the visual wavelengths. If we were to look in infrared wavelengths, so a longer wavelength, we're actually able to see what is behind the ISM cloud. So we can see that, of course, there are stars there, but in the visible, we see that the ISM completely blocks them. So when we are thinking about light that is traveling towards us through a cloud of dust, through a cloud of particles, such as the interstellar medium. We have to remember that we're seeing different wavelengths, or we're observing different wavelengths. We might not be seeing them with our eyes, but we can observe different wavelengths. So shorter wavelengths are more easily scattered. So short wavelengths, like in this diagram, the blue, which we know blue has a shorter wavelength than red, more easily scattered away by particles, meaning they bounce off something, they scatter in another direction. Longer wavelengths are much harder to scatter away. So if there's some scattering, the purple, the blue, the green wavelengths are going to scatter first before the red and the orange. So generally, the red will be able to make it through. So if we are looking at an area of stars and we see a large blob of stars that look red, we call this interstellar reddening, in that we're recognizing that the light from the star traveled through the ISM, traveled through a blob, a cloud of ISM, which scattered away all of the other wavelengths, so all we're left is the red wavelengths that were able to make it through. So these stars, they will appear to be more red to us. This we call interstellar reddening. So the scattering of wavelengths is actually something we observe every evening and every morning with sunrise and sunset. So blue light, if we're thinking about the visible, blue light is going to scatter more than red because blue has a shorter wavelength. So this is actually why our sky is blue. So here again we have an example of a star. Here's Earth. If we have our interstellar medium, a cloud of particles and dust, that is going to scatter the blue starlight away, and all that's going to be able to make it through is the red. So this would be a situation of the interstellar reddening, where the fact that we're looking at this starlight through the interstellar medium cloud, it's going to appear red to us. Very similarly to the way our sunlight appears to us on Earth throughout the day. So in the middle of the day, we are looking at the sun through the atmosphere. So here we're standing on the Earth, looking up at the sun. This would be noontime, right? So we're seeing all of the wavelengths. Blue is generally stronger, so we're going to see the blue more than the other wavelengths, even though we are receiving all wavelengths from the sun. This is where the sun is traveling through the smallest amount of atmosphere to get to us. However, if we were to wait until sunset, where now instead of the sun traveling through just this amount of atmosphere, because it's above our heads, it's now traveling through much more of our atmosphere to get to us, because the sun is about to set below our horizon. The sun is actually traveling through so much atmosphere, meaning so many particles in our atmosphere, that the blue light gets scattered away. And what we're left with are the reds and the oranges. This is why we have beautiful orange and pink sunrise and sunsets. Because as the sun is traveling through a longer portion of our atmosphere, a larger area of atmosphere, so it's traveling through this whole section. Note, this is not to scale. All the blue shorter wavelengths are going to scatter away. So all that reaches us are the red and the orange wavelengths, because the sun is the sunlight is traveling through so much more of the atmosphere. So it's a very similar concept when we think about light traveling through the interstellar medium, is that those shorter wavelengths are going to be scattered away. So if we look at some observations of this interstellar medium using a telescope, here we have this picture down here is the visual image. So here we see all sorts of stars on the outside. However, we see this blob of darkness. Now we know that this is not an empty area of space, but what we're actually seeing is the ISM blocking the stars behind it. And you'll notice that all the stars on the edge of the ISM are reddish. They kind of look orange in this picture. And that's because we're seeing these stars through only the edge of the ISM, so it's a much thinner area of ISM. We're going to see these stars appear much more dim and shifted to the red. Now, if we were to look at this same area of sky, instead of looking at visual wavelengths, we were to look at infrared wavelengths, we would in fact be able to see the stars that exist behind the ISM, and you'll notice that they have all been red shifted still. So, how do we measure this ISM? Okay, we can see it, we can map where it is, we can look at the interstellar extinction, but how do we actually learn anything about it? We can use absorption lines. So ISM also can produce absorption lines. And how we know this is we can look at absorption lines from stars that aren't quite right. Absorption lines from stars that don't make sense or don't add up with what we know about that star. And it can actually tell us what is in between us and that star, which would be the ISM. So for example, if we had an O star, very, very hot star, and it shows absorption lines of calcium and sodium, we know that that's not true because O stars are too hot to form these lines. So we must be looking at atoms that are in between the O star and Earth. We must be seeing the effect of atoms in between, which would be that ISM material. So whenever we have an instance like this where we know something doesn't add up, something isn't right with the absorption lines of the star that we're observing, we recognize that we are actually observing ISM in between ourselves and that star. So the ISM absorption lines look a little different than what we've been looking at from a star or the star's atmosphere. So the absorption lines that we've been noticing, that we've been talking about so far in this class from a star's atmosphere would have much more broad lines than ISM absorption lines. And that is because there is constant motion in a star's atmosphere. So there will be a bit of blurring of the absorption line for a star. So the star's atmosphere is going to be moving, there's motion, so there will be some blurring, meaning that the absorption line is going to be a little bit thicker. However, ISM atoms move very, very slowly, or barely at all, and they rarely collide. So if we were to look at an absorption line of a star, if we were to zoom in really, really closely on a spectral graph, if this is the absorption line of the star, which we've been looking at in class, we would have to zoom in even further to actually see the very, very narrow absorption lines from the interstellar medium. So they're very narrow in comparison to the spectral lines or the dip on the curve that we've been used to seeing from stars and stars' atmospheres. So, what makes up the ISM? I've been saying it's a cloud of particles, it's a cloud of dust. It's actually about 70% hydrogen, 28% helium, 2% other things. So similar to almost everything in space, it is hydrogen and helium. So what makes this unique is it is a cloud of this material. So it's a really dense, relatively cool cloud of these molecules. So atoms will join together and form molecules in this really, really dense, cool cloud of ISM. There's actually over 150 molecules that we know exist in clouds of ISM. And about 1% of the mass is what we call stellar dust. So carbon, silicates, ice, organics, iron, physical solid particles of dust, but they are absolutely teeny tiny. So they're less than 10 to the power of -6 meters. So very, 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 very small particles to stay suspended in this cloud. So about 1% of the mass of ISM are these teeny, teeny, tiny solid particles. So how can we continue measuring the ISM? So we can see the absorption lines, but what we can also do is look at the spectrum that is produced by looking at ISM. So if we're looking at an area of the ISM against a backdrop that is dark, or against a backdrop that also is cool, what we will see is an emission spectrum of the ISM. And we can actually detect this using a telescope that is set to observe wavelengths of a specific wavelength of 21 centimeters, which is within the radio wavelengths. So a long wave telescope that measures specifically 21 centimeter radio wavelength is going to pick up on the interstellar emission lines. So we're actually able to study the gases and the dust in between our stars that make up this ISM if we use this very specific wavelength with the telescope. So if we have a telescope that can observe specifically the 21 centimeter wavelength, we will be observing that interstellar emission. So here's an image of the radio wavelength of our galaxy. This is the 21 centimeter radio observation. So using a telescope that's just observing wavelengths of 21 centimeters, we're actually able to see this neutral hydrogen also is orbiting at the center of the galaxy. So that's a lot of hydrogen right there. And we are able to observe all of this ISM. So I have other versions of that same image. So this top one is the one we just saw. This is our galaxy in that 21 centimeter radio wavelength. If we look at the infrared wavelength, we're not seeing as much as the ISM. We're only seeing the cooler, less excited ISM material or gas and dust that is not quite as hot. The optical wavelengths, we do not see the ISM. We do see some dimmer blockage here. So this would be the, by optical, they mean visual. So in the visual wavelengths, we see that the dense area of ISM that is observed in the radio wavelength, we can see that it is causing some of that interstellar extinction, blocking some of the light in the visual. And then in the X-ray wavelength, so if we're looking only at the very, very short wavelengths, we see all the very, very hot, very excited gases in our galaxy. Generally, the large amounts of X-ray wavelength radiation is coming from gases that are being expelled by stars that are exploding. We will get into that a little bit more next week. So we have this ISM material, then what? So when we have clouds of this ISM material where the ISM begins to clump up, creating really dense clouds, we call this a nebulae. So nebulae means cloud in Latin. It is a dense area of dust and gas. So it is where ISM is the most dense. So nebulae, there's a couple different types. And really, the different types are characterized by how that region of ISM interacts with the nearby stars. So is starlight shining through? Is starlight shining on the ISM? It depends on the situation, is how we classify different types of nebulae. So an important component is ionized hydrogen. So remember, there's a lot of hydrogen in the ISM. So this HII is what we call is the symbol for ionized hydrogen, which is excited hydrogen atoms. So where we have regions of these really excited hydrogen atoms is where we have the clouds of this gas that have been ionized or excited by the UV radiation from nearby stars. So the reason that the hydrogen in the ISM can be ionized or be excited is because of the radiation from nearby stars. So this, when we have the ionization of the hydrogen, we're exciting that hydrogen. So the nearby stars are exciting the hydrogen within the ISM, which will, of course, then produce visible wavelength photons in the pink color. So remember that hydrogen always shows as the color pink. This is what we would call an emission nebulae. So it would look something like this, where we have this region of ionized hydrogen due to nearby stars. So the stars nearby this ISM are shining, sending their UV radiation into this cloud of material. The UV radiation is strong enough to excite the hydrogen atoms within the cloud, which will then emit photons in the pink visual wavelength. So it will actually look very pink, just like this. So this is what we call an emission nebula, where the ISM itself is emitting the photons. So it's always going to look pink because it is mostly hydrogen. And that when that hydrogen emits photons, we know they're going to look pink. So there is also what we call a reflection nebulae. So this is where we have non-HII regions, meaning we do not have ionized hydrogen. The hydrogen within the ISM is not being excited. It is not being ionized. It might still produce some light, though. So the stars around this ISM, in order to create a reflection nebulae, are not hot enough to ionize hydrogen. So in the emission nebulae, the nearby stars are causing this ionization, are causing the excitement in the ISM. They're causing the pink photons. In a reflection nebulae, which looks blue, the stars nearby aren't hot enough, or they're not close enough. So what we're actually seeing is the light from the nearby stars reflected off of the ISM. So the light is being scattered by really tiny dust particles that's within the nebulae, within that thick cloud of ISM. So the gas within the ISM is not excited, it's not emitting its own photons. Really what we're seeing is the light from nearby stars reflected off of the ISM. Why is it blue, you may ask? Because short wavelengths scatter easily. And the particles, in order to scatter these blue photons, they must be very, 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 very small, which in the ISM they are. The ISM has incredibly small particles that are able to scatter that blue light, showing us the blue light of the nearby stars. And then the third type of nebulae is called dark nebulae. So this is where we have the where we have the dense clouds of the ISM material that are blocking the stars behind. So this is, as I mentioned earlier, always in the visible wavelengths. So in the visible wavelengths, when we are observing the ISM, we see this dark material. We don't actually see the ISM, but what we see is where it exists because it's blocking what we should be seeing behind it. So generally, the dark nebulae are very irregularly shaped, and what we can actually observe are the currents and the sort of breezes that are moving through the cloud of ISM and pushing and shifting the ISM material. So this is called the Horsehead Nebula. It looks like a horse head. This here is called the Seahorse Nebula. Kind of looks like a seahorse. So there's many, many different nebula that are each named that we've observed thus far. When you see these dark nebula, know that you're looking at the visible wavelengths, and you're seeing where the ISM is actually blocking the light from the stars behind it.